So chapter 10 is all about acids and bases. So we will jump in to this section by talking about some definitions and how we classify our acids and bases in chemistry. Now normally my color scheme for pens doesn't really matter. For this chapter, I am going to use a specific set of pens. So red pen is going to represent my acids. And for the most part, throughout all of these lecture notes, anything that I write in red will deal with acids. Things that I write in blue are going to correspond to our bases. And then I'm going to reserve my green color pen for neutral compounds. And the reason for this color scheme is because we will learn that acids and bases can be determined by their pH or their acidity or basicity. We'll get to that later in this chapter. Will be determined by what's called litmus paper. And that litmus paper will turn either red for acids or blue for bases, and green or yellowish color is something that's going to be neutral. Okay. So if you are writing notes along with me, which I hope you all are doing, because part of learning is writing things out, hopefully that color scheme will help you kind of distinguish between the two different classes of our acids and bases. So basically, our acids and bases, what they are is just a specific class of chemical compounds. That's all acids and bases are. So we're not really necessarily introducing any new chemistry here. We're just talking about a more specific chemistry. So our first definition of our acids and bases, and just like equation and solution, I shorthand definitions DEF with an N as a superscript. You can choose whatever you would like there. So our first definition comes from very, very early on working with chemistry, and acids were defined as basically tasting sour. Whereas our bases, these were something that tasted bitter. Another helpful definition for bases on occasion, basically they are going to, oops, let's spell this correctly, leave your skin with a slippery feeling. And one of the reasons why it has this slippery feeling is basically some examples of bases are any soaps that you use. Okay, those are all bases. Another example of a base are your antacids or your, say, Tums. Okay. If you have an upset stomach or have acid reflux, you know what Tums are. For acids, some examples of this would be, say, your citrus fruits. Or if we're looking at, say, still household items, vinegar is an acid. Okay, that's acetic acid. That might be worth us writing down. By the way, while I'm thinking about it, in section 10.1, your book goes through how to name acids. Don't worry about that. We're not going to do any naming of acids. I won't require you to know the names of acids. Just be aware that when you work through the QMP and work through sapling site, it may assume that you know names or formulas from names. So just look them up on a test. I will give you any formulas that you need. So this is our first kind of working definition of what, how we classify between the acids and the bases. But hopefully by just looking at these definitions, we realize that there's a problem right away, and that this basically requires us to taste or consume chemicals. Okay, which is never a good idea. We never want to eat the chemicals. So Arrhenius came by, a scientist, and he basically kind of built on this definition. And he looked at it from, okay, how can we define these and, live to tell the tale? So he looked at the formulas of these, what acidic compounds looked like and what basic compounds looked like. And he determined that acids are going to produce an H plus, which we call a proton. So it produces an H plus when it is dissolved in water. So that's our definition from Arrhenius. His definition of bases were that they produce a hydroxide ion when dissolved in water. So those were his main differences between there. Okay. So our OH minus here, we've seen this before. This is one of our polyatomics. Okay, this is our hydroxide ion. And we're going to see this a lot this chapter. Our H plus, this is basically it's a hydrogen ion. Hydrogen has one proton and therefore in its element form has one electron. When it loses that one electron, it becomes the hydrogen ion. And since its nucleus only has one proton, if it loses that electron, all this is a proton. Okay, there's no electrons, there's no neutrons, it's just a proton. So a lot of times we just call this a proton. Now, one of these key things to this definition that I want to point out here is that in order to have an acid or a base, we have to be dissolved in water. Oops. So what that means is for our acids and bases, okay, it has to be something that's going to be soluble in water, and therefore we're going to be looking at things in the aqueous phase. Okay. Now this is not exclusive. We're just dealing kind of with the basic acids and bases, kind of our starting point. So all of our acids and bases are going to be dissolved in water. Okay. So what that means for us with this hydrogen ion is the hydrogen ion, or this proton, doesn't actually exist by itself in this fashion. Okay. What happens is if we have this H plus, since water is present, okay, these form together to form H3O plus. Okay. This H3O plus, this is called the hydronium ion. And in chemistry, basically, if we write down H plus for an equation for anything when we're talking about acids and bases, what we really mean is H3O plus. Okay, so we take these to be the same, even though technically they're not. Okay, but for our discussion, we can basically look at them as the same. Sometimes for how we're looking at an equation, this is going to be easier for us to use, whereas other times in equation, this will be easier for us to use. So just know that these are the same thing. All right, now one of the problems with Arrhenius's definition, he had it basically on par when he was talking about acids, but the problem was there are a lot of components, there are a lot of chemicals that had basic properties that didn't produce a hydroxide ion. Okay. So Arrhenius' definition, definitely a step up from our first definition, but was not all inclusive of our acids and bases. So our working definition that we're going to use in this class comes from Brønsted and Lowry. And it's possible, I've seen this definition just listed as Brønsted definition. I've seen it listed as just Lowry definition. I learned it as the Brønsted-Lowry definition, so you could see it in multiple different ways, just as a heads up. But the definition is always the same regardless of the name of what it's called. The Brønsted-Lowry definition of an acid is that it's going to donate an H plus, a proton, and our base is going to accept a proton. So now, with our Brønsted-Lowry definition, okay, we are going to use this definition, okay, for this class. Is the key now is this hydrogen ion. So key to acid base is an exchange of a proton. All right. So let's talk about now a different type of kind of our acids and bases, a different term. One term is our conjugate base. And I think what I'm going to do is I'm going to put an end to our collimated notes here. And let's talk about our conjugate base. Oops. Our conjugate base is going to be the result from an acid losing a proton. So if we look at an example here, we want to know what is the conjugate base for HCO3 minus. So HCO3 minus is an acid in this case. Okay. We're going to write the conjugate base, which is the result from our acid losing a proton. Okay. So our acid here is going to lose a proton. So it's going to remove that hydrogen out front, which means what we are left with is CO3. This molecule was negatively charged overall. Okay. And we lost a proton, so we lost a positive charge, meaning that this got more negative. So we have CO3 2 minus, which should look familiar to us because that is the carbonate ion. This here is our conjugate base. So let's look at another example. Okay, maybe try this on your own. What is the conjugate base of HNO2? Go ahead and pause the video, try and work that out yourself, and then I'll have the answer when you come back. So we have HNO2, and this is our acid, and we know that, besides the fact that we're asking for the conjugate base, but we know that by this hydrogen out in front. That hydrogen out in front means or indicates to us that we have an acid. So this acid is going to lose a proton, which is going to leave us with NO2. And we lost a positive charge, which means that since this started out as neutral, if we have a positive charge here, we need a negative charge on the NO2. So this is our conjugate base. All right, we can do the same concept here for conjugate acids. So this is going to be the result from a base gaining a proton. So if we look at an example here, let's look at what is the conjugate acid for F minus. So we have F minus is our base, and we're going to gain a proton, and we're going to gain an H plus, and that's going to form our conjugate acid. So remember, acids, I said, have their hydrogen listed first, so we'd form HF, and this is our conjugate acid. All right, Now let's look at another example. Try this one on your own. What is the conjugate acid for HCO3 minus? All right. So we have HCO3 minus. Okay. Right now this is going to act as our base because we want to write our conjugate acid. So we're going to add our proton. That proton gets added out in front. We already have one there, so we add a subscript of 2 because we are adding another hydrogen. And we have H2CO3. Originally it was negatively charged. We're adding a positive charge, so that's going neutral. And this is our conjugate acid. All right.